So in this video, we're going to talk about how do we actually draw the shorthand configurations for Lewis structures. And the idea here is that we use the shorthanded formula because for simple Lewis structures, for simple electron configurations such as, let's say, lithium or beryllium, it's pretty simple. But when we get to more complicated stuff like bromine or uh, potassium, calcium, you may find it really helpful that we could actually use what we call the shorthand formulas. And so how do we do that? Let's do a quick example, right? And so because you're watching this video, I'm assuming at this point you're kind of some sort of proficient with um, writing electron configurations. But let's do the electron configuration for sodium real quick. So how do we do the electron configuration for sodium, right? And the idea, and let me delete this. How do we do the electron configuration for sodium? So let's say we want to do the electron configuration for sodium. Well, we simply start with the first column, so this would be 1s. I count hydrogen and helium, so that is 2 electrons. I go down to the second column, and this would be 2s, because I see lithium and beryllium in the s block, so this would be 2s2. I go across where I'm in the p block because I'm still not done with the second column, and I go all the way to neon, and that would be 2p6. And then in the third column, I have 3s1 because sodium is right there. That's the first electron within the third row. So this is the electron configuration for sodium. Now you could see how this is kind of okay, a little bit cumbersome. It's only 4, so it's not really bad. But when we start getting to stuff like bromine, etc., stuff becomes too long and we just don't want to deal with it. So how do we actually deal with it? Let's say we want to write the shorthand configuration for sodium. How do we do it? Well, what we simply do is we look at the element of interest and we take the noble gas that is immediately above the element of interest. So in this case, where are noble gases? Or noble gases are all these things right here. These are noble gases. And so we take the noble gas that is immediately above the atom of interest. So in this case, sodium is the is the element of interest. The noble gas directly above it would actually be neon. Right? So neon would be the noble gas above it. So how do you write it? We take our noble gas and we put it in parentheses or brackets. So in this case, it would be neon. And then we simply fill in the electrons that we have remaining, right? Neon takes care of the 10 electrons. Neon takes care of the 10 electrons that we wrote right here. And I'm going to show you how it actually does that, right? So in this case, the shorthand formula for sodium would be neon 3s1. All we did was just fill in the remaining electrons that were left over. Now, if you look at it, you'd say to yourself, well, how does this make sense? Because look, in our long-handed formula, we have these numbers correspond to the number of electrons, right? Remember, the S and the P corresponds to the block, and these bigger numbers in front corresponds to the column, the row that we're in, right? So look, we have 2, 4, and 6. So if we take 4 plus 6, that is equal to 10. And in fact, that is what neon took care of, right? So if we count all the way and follow me, from hydrogen we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So there goes the 10 electrons that that neon took care of for us, right? So the only other one we had to fill in was the 3s1, and in fact, that would be 11 electrons total, which would be what sodium has. And if you look, interestingly, the number of electrons it's kind of hard to see, but right here you actually have an 11 um, for the number of electrons for sodium. So let's try a couple more. Let's say we want to do, uh, calcium, right? How would you do calcium, right? Well, I'm gonna quickly write out the long-handed formula, and then we're going to compare the short-handed formula, which is really what we're talking about. So for calcium, this would be 1s2, 2s2, 2p6, right? Because we're in the second column, going all the way to neon. Now I'm in the third column where it has the sodium and magnesium, so this is 3s2, and I have to go 3p6 to go all the way to argon before I eventually hit calcium, which would be 4s2. Right? So this is the long-handed formula for calcium. Now, what is the short-handed formula? Well, I'm going to take the noble gas directly above calcium. So in this case, calcium is right here. The noble gas directly above it would be argon. So I'm going to write argon in brackets. Right? And whatever that is left over is what I got to fill in. So argon took care of everything above. Argon took care of every electron above it. So the only thing I'm missing from argon, I want to continue. I'm going to be in the fourth column, so that is 4. I'm in the S block, so this is 4s, and I count 1, 2, so this is 4s2, and so this would be the shorthanded formula for calcium. Again, if you want to double check, you would see that argon actually took care of all these electrons right here, except the 4s2, right? So it actually took care of 2, 4, this would be 10, this would be 6, this would be 2, so that would be 18. And in fact, you'd actually see that right at this, if you look on a bigger periodic table, you would see that this number right here is actually 18. Right? And so that would be the shorthanded formula for calcium. Let's do a simpler one. Try this one. How about the shorthanded formula for beryllium? How do we do it? Well, I'm going to look at beryllium. I'm going to look at a noble gas directly above it, which in this case would be helium. Right? So this would be helium, and I have 2s2. Right? So again, in this case, this would be the shorthanded formula for beryllium. Now, beryllium has a total of 4 electrons, and it should make sense that helium has 2 electrons, and here's our other 2 electrons that we're missing. And so, guys, this is how we actually draw or write the shorthanded formulas for or electron configurations.